A cosmic nursery glows with violent beauty just 1,500 light-years away. The Orion Nebula holds more than just newborn stars. It conceals bizarre secrets that defy our basic grasp of how the universe works. By the end of this journey, you will know 30 of its most stunning and unexplained phenomena. We will explore how entire planetary systems are being ripped apart before they can even form, and why some stars are catapulted into the void at incredible speeds. What does it feel like to witness the raw, chaotic birth of worlds? At the very heart of this glowing cloud lies a stellar powerhouse known as the Trapezium Cluster. 4 brilliant, massive stars form its core, each one a celestial newborn just 1,000,000 years old. But do not mistake their youth for gentleness. These stars are colossal, burning ferociously and unleashing a hurricane of ultraviolet radiation. This invisible energy is so intense it acts like a cosmic blowtorch, boiling away the surrounding gas and carving vast, empty cavities into the nebula itself. The process is one of breathtaking violence. As the radiation slams into the cooler gas at the edges of these cavities, it creates immense shock fronts, walls of superheated material that glow with a fierce, beautiful light. It is a continuous demolition and construction site on an unimaginable scale, where the very forces that give life to new stars are also tearing the stellar nursery apart. This radiant fury is what sculpts the nebula's iconic shape, a constant battle between creation and destruction happening right before our eyes. Surrounding this stellar fury, the Hubble Space Telescope has uncovered hundreds of seemingly delicate objects. We call them proplyds, short for protoplanetary disks. These are the birthplaces of future solar systems, vast spinning platters of gas and dust that swirl around infant stars. Within them, microscopic dust grains are slowly, patiently clumping together, beginning the multi-million-year process of building planets. But here in the Orion Nebula, these fragile nurseries face an existential threat. The intense ultraviolet radiation from the trapezium stars is literally boiling them away. This process is called photoevaporation. Imagine a child trying to build a sandcastle as an incoming tide relentlessly washes the sand out from under them. That is the dramatic race unfolding here. The proplyds are caught in a cosmic tug of war. On one hand, gravity is trying to pull the material inward to form planets. On the other, the stellar radiation is blasting it away into the void. The Hubble images show this destruction in stunning detail. Many of the proplyds appear as teardrop-shaped clouds, with long, comet-like tails of gas being stripped away by the stellar wind. The side facing the trapezium is compressed into a bright, glowing wall, a direct shock front from the radiation, while the opposite side streams out into a fading trail. This is the ultimate deadline. For a proplyd, it is a desperate race against time. Can planets coalesce from the chaos before their very building blocks are evaporated into nothingness? Some of these disks will succeed, giving birth to new worlds, while others will be utterly dismantled, their potential for life snuffed out before it even began. These violent winds from the newborn stars do not simply fade into the void. They collide with the slower moving gas of the nebula, creating immense, arching structures that glow against the cosmic backdrop. These are bow shocks, and they act as cosmic weather vanes, revealing the invisible dynamics of the interstellar medium. A bow shock forms in much the same way that water piles up in front of a speedboat, or how air compresses rapidly ahead of a jet flying faster than sound. Here, the speeding stellar wind, a stream of charged particles racing outward from the star, slams into the more placid, ambient gas of the nebula. The result is a titanic collision. The gas at the interface is compressed, heated to extreme temperatures, and set aglow, tracing out a vast, arcing wall in space. The shape of these arcs tells a clear story. They are not symmetrical bubbles. Instead, They curve around the star, pointing directly away from the source of the strongest opposing flow of nebular material. By mapping the orientation of these bow shocks, astronomers can essentially read the currents within the nebula, charting the flow of this interstellar atmosphere as it moves around the powerful stellar engines. It is a visible record of an otherwise invisible force, a stunning snapshot of the complex weather patterns that govern this celestial nursery. Even in a place famous for brilliant starlight, some of the most intriguing objects are those that never truly shine. Scattered throughout the Orion Nebula is a vast population of cosmic underachievers known as brown dwarfs. These are strange, shadowy bodies caught in a perpetual identity crisis. They are too massive to be classified as planets, yet they lack the sheer heft to ignite the sustained nuclear fusion in their cores that defines a true star. A brown dwarf is, in essence, a failed star. Their formation begins just like their stellar siblings, from a collapsing cloud of gas and dust, but somewhere along the way, the process stalls. The object simply does not accumulate enough mass to reach the critical pressure and temperature needed to fuse hydrogen, the main engine of every star like our Sun. So what happens to them instead? They form, they cool, and they simply fade into a long, dark existence, glowing faintly only with the leftover heat from their violent birth. Their surface temperatures can be surprisingly Earth-like, yet they are nothing like a planet. They are solitary, self-formed, and fundamentally incomplete. So why do these cosmic failures matter so much to astronomers? Their very existence helps us define the lower boundary of star formation. They are the missing link between the most massive gas giant planets and the smallest, dimmest red dwarf stars. By counting them and studying their properties, scientists can test theories about how gravity assembles objects in the universe. Is there a minimum mass required to make a star, or is the process more like a continuum, producing a full spectrum of objects from true stars to these dim, drifting embers? The Orion Nebula, with its rich and diverse population, provides a perfect laboratory to find the answers. Every brown dwarf discovered pushes our understanding further, forcing us to ask where we draw the line between a planet and a star, and what it truly takes to light a fire in the cosmic dark. Yet even the faint glow of brown dwarfs is not the strangest light in this nebula. Deep within the dusty heart of Orion lies an object that shines with an unusual secret. Known as the Becklin-Neugebauer Object, it appears as one of the brightest sources of infrared radiation in the entire region. But why would something so luminous hide in the infrared part of the spectrum? The answer is a thick, nearly impenetrable shroud of cosmic dust. This dust absorbs almost all of the object's visible light, heating up until it glows with a fierce thermal heat that we can only detect as infrared. Peering through this dusty veil, astronomers believe the object is actually a massive young star, perhaps 20 times the mass of our own Sun, but its story gets even more peculiar. Careful observations have revealed that this shrouded giant is not sitting still. It is moving, and moving fast. Its trajectory, its path through space, points directly backward, like a cosmic arrow, straight toward the nebula's most violent core. This is the signature of a stellar ejection event. Imagine a gravitational slingshot within the crowded Trapezium Cluster, where a close encounter between several massive stars flung one of them outward at tremendous speed. The Becklin-Neugebauer Object is that celestial outcast, a runaway star catapulted from its birthplace and now plowing through the surrounding gas and dust. It is a brilliant fugitive, fleeing the scene of its own violent birth, and its motion provides a rare, frozen moment of evidence for the chaotic dynamics that govern even the youngest of stars. This stellar violence is not a one-way street. As new stars form, they often fight back against the nebula itself. The result is one of the most visually stunning phenomena in all of astronomy, the Herbig-Haro object. These are not stars, nor are they the traditional clouds of a nebula. Instead, they are glowing, wispy patches of nebulosity that look like cosmic fireworks frozen in mid-explosion. Their beauty, however, is a direct product of fury. Each Herbig-Haro object is a shock front, a titanic collision in space. They are created when narrow, high-speed jets of ionized gas, ejected from the poles of a newborn star, slam directly into the surrounding cloud of gas and dust at velocities that can exceed 100,000 miles per hour. The collision is so violent it superheats the material, causing it to glow with an intense, radiant light. It is like a celestial blowtorch igniting a cloud of hydrogen, creating temporary, evolving sculptures in the void. These jets are a fundamental part of the star formation process. As a young star gathers mass from its surrounding disk, not all of that material falls onto the star itself. Some of it is channeled by powerful magnetic fields and hurled back out into space from the star's north and south poles. These jets act as a release valve for the system's immense angular momentum, a way for the star to shed excess energy as it grows. What we see as a beautiful, glowing knot is actually the working end of this cosmic engine, and these structures are not static. They change, evolve, and even move over just a few years. Astronomers have observed individual Herbig-Haro objects shifting position, new knots of glowing gas appearing as the jet plows through different densities of interstellar material. It is a dynamic, real-time demonstration of the violent forces that accompany the birth of every star, a breathtaking fountain of energy shooting out from the celestial cradle. This bright, sharp-edged structure known as the Orion Bar is not a solid object at all. It is a cosmic battle line, a visible frontier where two utterly different realms collide. On one side, you have the blistering ultraviolet radiation from the trapezium stars. On the other, a cold, dark cloud of molecular hydrogen, the raw material for building new stars. The bar itself is the glowing, turbulent interface where these forces meet, a region scientists call a photodissociation front. Imagine a shoreline where the ocean of light from the stars crashes against the continent of cold gas. This is the edge of the trapezium's influence, the point where its power finally begins to wane. The intense radiation slams into the molecules of the dark cloud, but here, it no longer has enough energy to completely strip electrons away and create the ionized plasma found deeper in the nebula. Instead, it performs a different kind of cosmic chemistry. The ultraviolet light has just the right energy to break apart the tough molecular hydrogen, splitting these two atom molecules into individual, highly reactive hydrogen atoms. This process of photodissociation gives the region its technical name and unleashes a cascade of chemical reactions. The Orion Bar is essentially a massive, natural laboratory for interstellar chemistry. Within its narrow, brightly glowing zone, simple molecules are shattered by starlight, and the resulting atoms eagerly recombine into new, more complex forms. It is here that astronomers have detected a rich inventory of molecular ingredients, including water, carbon monoxide, and even simple organic compounds. This makes the bar a crucial subject of study, a place where we can watch the fundamental building blocks of life itself being forged and destroyed in the harsh environment of a stellar nursery. The precise structure of the bar, its thickness and brightness, tells a detailed story about the strength of the starlight and the density of the gas it is eroding. We are watching the nebula actively reshape itself, one chemical reaction at a time. But the brilliant nebula we see is merely the surface of a far deeper cosmic structure. Behind the glowing gas and shining proplyds lies the true giant of this region, the vast and cold Orion molecular cloud. This is the nebula's dark, silent parent, an immense reservoir of gas and dust so dense it blocks the light from background stars. Within this sprawling cloud, one particular knot of matter stands out, a region known as Orion Molecular Cloud 1. This dense core is a stellar factory operating in near total secrecy, its most dramatic labors hidden from our optical telescopes by a thick blanket of cosmic soot. Here, the temperature plunges to just a few tens of degrees above absolute zero. In this frigid, dark environment, gravity works undisturbed, slowly and relentlessly pulling the gas and dust together into ever tighter clumps. These are the seeds of future stars, some of which will one day outshine the entire Trapezium Cluster. To peer into this hidden realm, astronomers must use different eyes, telescopes that see in the radio and infrared parts of the spectrum. These wavelengths can pierce the obscuring dust, revealing a chaotic scene of raw creation, instead of the elegant, evaporating proplyds seen in the nebula's harsh light. The inner core of Orion Molecular Cloud 1 is a tangled mess of filaments and knots, where gravity is the only architect that matters. This is star formation in its most primitive and shielded state, a process that serves as a universal blueprint. The violent, radiation-filled nursery of the visible nebula shows us one extreme of stellar birth, a frantic race against time. In contrast, the quiet, dark core of Orion Molecular Cloud 1 shows us the other, a slow, patient accumulation of matter in near total isolation. By studying both environments, we get a complete picture of how stars are born across the universe, from the most chaotic clusters to the most solitary suns. This dark core is a reminder that for all the brilliant spectacle of the Orion Nebula, the most fundamental work of creation often happens in the dark, hidden from view until the new stars themselves finally push back the cosmic dust and shine. The chaos of stellar birth does not confine itself to the nebula's glowing borders. Some stars are born only to be immediately exiled, cast out into the galactic darkness. These are the runaway stars, stellar projectiles flung from their cradle by the very violence of their origins. The primary suspect for this cosmic ejection is a gravitational slingshot. Within the densely packed core of the Trapezium Cluster, young, massive stars dance in a frantic gravitational ballet. When two or more of these stellar heavyweights pass perilously close to one another, their immense gravitational fields can interact like a complex catapult. One star might absorb the orbital energy of the others, getting a tremendous boost that sends it racing away at speeds that can exceed 100,000 miles per hour. The evidence for this is written in their motion. Astronomers have identified several stars, like the brilliant Aorigine, whose trajectories, when traced backward through time, point directly to the heart of the Orion Nebula. It is as if we are seeing the lingering contrail of a celestial bullet fired over 2 million years ago. These stellar fugitives do not travel alone. Their immense gravity can pull any fledgling planetary systems along with them, though the violent ejection would likely shred delicate protoplanetary disks. A planet surviving such a journey would find itself on a lonely voyage, hurtling through the cold void between stars, its night sky forever changing as its parent star carried it further from the familiar stellar neighborhood of its birth. The existence of these runaways reveals a fundamental truth about star formation. The nurseries that give stars life are not gentle places, but turbulent, competitive environments where gravitational chaos can dictate a star's ultimate destiny, casting it out into the infinite sea of space. Scattered throughout the nebula like frozen droplets are countless strange, compact objects known simply as knots. These are not stars, nor are they the wispy tendrils of background gas. Each knot is a dense, localized concentration of gas and dust, so thick it appears as a small, dark smudge against the nebula's brilliant glow. Their composition is a complex mix of molecular hydrogen, the primary building block of stars, along with a rich frosting of heavier elements and complex molecules that have condensed onto the tiny, cold dust grains within them. These knots are cosmic seeds, but their ultimate fate is a subject of intense debate. Some may indeed be the earliest stages of star formation, dense cores where gravity is just beginning its slow, patient work of pulling material together. Given enough time and isolation, a knot like this could collapse under its own weight, eventually igniting into a new star. Yet many of these knots appear to be located in regions that have already been scoured by intense stellar radiation, places where the delicate process of star formation should have been disrupted long ago. This leads to another, more violent possibility. Perhaps these are not seeds at all, but the shrapnel from ancient stellar explosions or the shredded remnants of larger clouds that were torn apart by the trapezium's fierce winds. They could be the surviving cores of structures that were otherwise evaporated, the last dense knots of material holding on against the eroding power of starlight. Their very existence poses a fundamental question. Are we looking at the beginnings of new solar systems, or the ghostly tombstones of systems that never were? Each knot is a tiny mystery, a potential future sun, or a relic of past chaos, and their abundance makes the Orion Nebula a living archive of its own turbulent history. Beyond the individual dramas of runaways and failed stars lies the grander story of the community itself. The Orion Nebula cluster is a sprawling metropolis of thousands of stars, all bound together by gravity, and all sharing a common, surprisingly youthful age of just about 1 million years. This makes it a perfect snapshot of a stellar nursery in its fiery infancy. Yet even in this cosmic toddlerhood, a clear social hierarchy has already emerged. The most massive, brilliant stars have predictably migrated to the crowded downtown core, the region centered on the trapezium. This process is known as mass segregation, a gravitational sorting where the heaviest stars sink to the center of the cluster through dynamic interactions with their lighter neighbors. Think of it like a cosmic dance where the biggest dancers gradually push their way to the middle of the floor, drawn by the collective pull of the crowd. This is not a gentle process. It is the result of countless close encounters and gravitational tugs, a slow-motion reorganization that happens within the first few million years of a cluster's life. By studying this structure, astronomers gain a crucial key to understanding the ultimate fate of all such open clusters. Most of them are not permanent structures. They are temporary stellar families, held together by a fragile gravitational glue. Over tens or hundreds of millions of years, the relentless gravitational pulls from outside stars and the tidal forces of the galaxy itself will gradually strip these clusters apart. Their member stars will drift away, joining the vast population of solitary suns in the galactic disk. The Orion Nebula cluster is our closest and best laboratory for watching this process begin. We see the initial conditions, the raw density of stars, and the early stages of mass segregation that will ultimately determine how long this family stays together before it dissolves into the background of the Milky Way. Watching this cluster is like reading the first chapter of an epic novel, one that tells the story of stellar birth, life, and the eventual diaspora that seeds the galaxy with suns. That sharp, luminous edge of the Orion Bar is more than just a beautiful boundary. It is a cosmic stage where the fundamental process of photoevaporation plays out on a truly monumental scale. While we have seen this effect destroying individual protoplanetary disks, here it is happening to an entire molecular cloud. The bar's bright ridge is the direct result of the trapezium's radiation slamming into a dense wall of gas and dust. This is not a gentle erosion. It is a ferocious, continuous stripping away of material, as the ultraviolet light systematically blasts molecules apart and heats the gas until it streams away into the vacuum. The entire structure is essentially evaporating before our eyes, but at a pace so slow and vast, it creates a seemingly permanent, glowing front. This makes the bar a perfect natural laboratory. Astronomers do not need to simulate these conditions in a computer model. They can simply observe this single, sharp edge to understand how intense starlight shapes and ultimately destroys the clouds that give it birth. By measuring the bar's thickness, its brightness, and the speed of the gas flowing away from it, they can calculate the precise rate of this cosmic demolition. It is a slow-motion disaster of breathtaking scale, revealing how the life cycle of a nebula is a constant balance between the gravitational pull inward and the radiant pressure pushing outward. The Orion Bright Bar is the ultimate expression of that pushing force, a brilliant but destructive wave slowly washing over a continent of cold, dark gas. Even the nebula's brilliant light cannot penetrate its deepest shadows, darker than the space between stars. Immense columns of cold dust and gas snake through the region, appearing as stark silhouettes against the glowing background. These are not empty voids. They are infrared dark clouds, the coldest, densest places in the entire stellar nursery, and they are hiding the future. To our optical telescopes, these clouds are simply blackness, an impenetrable curtain. But when we switch our view to the infrared and submillimeter wavelengths of light, a hidden world emerges. These longer wavelengths slip between the dust grains like a whisper, revealing the incredible truth. Within these dark columns, the temperature plunges to just a few degrees above absolute zero. In this profound cold, gravity works without interruption, patiently pulling the gas and dust together into ever tighter knots. Each of these knots is a prestellar core, a dense pocket of matter that is the direct precursor to a new star. This is star formation in its most primordial state, a process happening in near total secrecy, shielded from the violent radiation that is evaporating the nebula's other, more exposed protoplanetary disk. The material here is so thick, so rich with molecular gas, that it can birth stars far more massive than our own sun. These infrared dark clouds are the ultimate cosmic reservoirs, the protected vaults where the next generation of stellar giants is quietly taking shape, completely hidden from the brilliant chaos that surrounds them. The Orion Nebula is not the static portrait it appears to be. Historical records reveal a stunning secret. Astronomers from centuries past, including the famed William Herschel, documented the nebula as significantly brighter and more expansive than we see it today. This is not a trick of memory or imperfect telescopes. The nebula itself has been dimming, its glow fading over the span of human observation. How can a structure 1,500 light-years across change in a mere few hundred years? The explanation lies not with the stars themselves, but with the intricate cosmic veil hanging between us and them. The leading theory points to subtle shifts in the foreground dust. Imagine a vast, delicate curtain of fine soot drifting slowly in front of a brilliant stage light. Even a slight rearrangement of these microscopic dust grains can dramatically alter how much light passes through. A region that was once transparent can become opaque, or a dense patch might thin out, causing a different part of the nebula to brighten. This dust is not a solid wall. It is a dynamic, swirling medium, its density and distribution constantly influenced by the very stellar winds and radiation pressures we have been exploring. The changes we witness are a real-time demonstration of the nebula's ongoing evolution, a slow-motion dance of shadow and light on a truly cosmic stage. This variability forces us to confront a profound idea. The universe is not a museum exhibit frozen in time for our observation. It is a living, breathing entity, and we are catching a fleeting glimpse of its perpetual transformation. While the nebula's outer layers boil away under intense starlight, a more primal struggle unfolds deep within its darkest cores. Here, buried in the cold, dense heart of infrared dark clouds, newborn protostars are fighting their way out of their own dusty wombs. Their primary weapon in this cosmic birth is a phenomenon of staggering scale, molecular outflows. These are not the thin, ionized jets that create Herbig-Haro objects, but something far more massive and expansive. Imagine a protostar as a frantic engine at the center of a collapsing cloud. As it rapidly pulls in enormous amounts of gas and dust, not all of that material can fall onto the star itself. The system's rapid spin and powerful magnetic fields funnel some of the infalling matter into two powerful, opposing channels that blast outward from the protostar's poles. These are the molecular outflows, colossal rivers of cold gas that can stretch for several light years in each direction. We are not talking about a gentle breeze. These outflows move at tens of thousands of miles per hour, and they carry enough mass to make entire stars. They are bipolar, shooting out in two perfectly opposite directions, carving vast tunnels through the surrounding molecular cloud. This violent process is not just a side effect of star formation. It is absolutely essential. Without these outflows to carry away excess energy and angular momentum, a protostar would spin itself apart before it could ever stabilize. More importantly, these titanic flows act as a fundamental regulator for the entire stellar nursery. By physically pushing against the surrounding gas cloud, the outflows disperse the very material that feeds further star formation. It is a self-limiting mechanism. A single protostar, through the sheer force of its own birth, can clear out a vast volume of space, shutting down the creation of potential sibling stars nearby. This is the ultimate paradox of creation, where the violent act of one star's birth can dictate the fate of countless others, ensuring that stellar nurseries do not give birth to an infinite number of suns. The same violent radiation that tears apart protoplanetary disks is also a master chemist, forging complex molecules in the chaos. Deep within the glowing gas of the Orion Nebula, radio telescopes have identified a startlingly rich inventory of chemical compounds. We are not just talking about simple hydrogen and helium, the basic elements of the universe. Astronomers have detected the distinct spectral signatures of water, carbon monoxide, and a host of other, more complex organic molecules. The term organic here does not mean life, but it does mean carbon-based, the fundamental scaffolding upon which all life as we know it is built. These molecules are the precursors to the building blocks of life, things like amino acids and sugars. How can such delicate structures form in an environment flooded with destructive ultraviolet light? The answer lies in the unique conditions of the nebula itself. The process begins on the surfaces of microscopic dust grains. These tiny particles, finer than smoke, act as miniature laboratories and sanctuaries. In the cold, dark depths of the molecular cloud, simple atoms like carbon and oxygen stick to these dusty surfaces. Over time, they slowly shuffle and combine, building up into more complex molecules. When a shockwave from a nearby stellar explosion or the radiation from a newborn star heats the dust grain, these newly formed molecules are released back into the gas, where we can detect them. It is a continuous cycle of construction and destruction, where the very energy that shatters molecules also provides the heat needed to drive new chemical reactions. This makes the nebula a vast, natural chemistry set, one that is constantly producing the raw ingredients for life. The implications are profound. If nebulae like Orion are cosmic factories for probiotic molecules, then the fundamental components for biology could be scattered everywhere new stars and planets form. The seeds of life, it seems, are sown in the same stellar furnaces that forge the elements themselves. Some of the most direct evidence for planet formation appears not as light, but as shadow. Scattered across the bright canvas of the nebula, astronomers have spotted dozens of perfect, dark circles. These are not holes in the fabric of space, but silhouette disks, protoplanetary systems seen from the side. When a disk of gas and dust orbits its star in a perfectly edge-on alignment from our perspective, it creates a stunning visual effect. The central star might be completely hidden by the thick, dusty midplane of the disk, while the disk itself blocks the brilliant background light of the nebula. The result is a crisp, black circle suspended against the glowing gas, a cosmic silhouette that reveals the disk's shape and size with incredible clarity. It is a direct, almost architectural view of a construction site. While the evaporating proplyds show us the tragic fate of some systems, these silhouette disks show us the pristine, untouched materials before the chaos begins. They are the raw, unprocessed feedstock for building planets, frozen in a moment of perfect alignment. Their darkness is not emptiness, but density, a testament to the sheer amount of solid material already coalescing around these infant suns. Each one is a snapshot of a potential solar system in its earliest, most vulnerable stage, a dark coin spinning in a sea of light, holding within it the possibility of worlds. This cosmic chemistry set is stirred by a hidden, chaotic energy. Deep within the Orion Nebula, the gas is not simply drifting. It is churning with supersonic turbulence, a frenzy of motion that shapes the entire nursery. Astronomers measure this chaos not by watching individual particles, but by listening to the light itself. When they analyze the nebula's spectrum, the unique fingerprint of its glowing gas, they find the spectral lines are not sharp and narrow. Instead, they are broadened and blurred. This blurring is a direct result of the gas moving at wildly different speeds, some toward us and some away, all at once. The collective motion is so violent, it creates a sonic boom on a cosmic scale, with internal motions far exceeding the speed of sound. This is not a gentle simmer. It is a supersonic maelstrom. This turbulence has a profound influence on the nebula's destiny. On one hand, it acts as a supporting force, creating a kind of chaotic pressure that helps hold vast clouds of gas together against the crushing force of their own gravity. Without this turbulent support, these clouds would collapse into stars far too quickly and efficiently. Yet, this same turbulence can also be a destructive force. It creates shock waves that rip through the gas, compressing some regions into new stellar seeds, while simultaneously tearing other structures apart. It is the reason the nebula looks so filamentary and complex, its glowing tendrils and dark lanes sculpted by these invisible, supersonic winds. The entire structure is a snapshot of a battlefield where gravity tries to pull things together and turbulence works to fling them apart, a fundamental conflict that dictates the pace of star birth and the very architecture of the cosmos. That brilliant red glow defining the Orion Nebula is not a simple reflection. It is a cosmic light show, a transformation of energy happening on an atomic scale. The process is called fluorescence, and it turns the entire nebula into a vast natural lamp. The key player is the simplest and most abundant element in the universe, hydrogen. The gas cloud is flooded with the invisible, high-energy ultraviolet radiation pouring from the trapezium stars. When a photon of this ultraviolet light strikes a hydrogen atom, it delivers a powerful jolt of energy. This energy is absorbed by the atom's single electron, kicking it into a higher, unstable energy level, like lifting a ball to the top of a hill. But this excited state cannot last. Almost instantly, the electron falls back down to its stable, ground state. It cannot, however, return all that energy in one go. The energy is released in smaller packets, as new photons of visible light. Crucially, these new photons are less energetic than the original ultraviolet ones that started the process. This shift in energy changes the color of the light from invisible ultraviolet to a very specific, visible red. This particular red glow is known to astronomers as hydrogen alpha light, and it is the primary reason the Orion Nebula paints the sky with its characteristic crimson hue. It is a continuous cycle of absorption and re-emission, where the violent, invisible energy of massive stars is downshifted into the beautiful, visible radiance we can see from Earth. This is the fundamental physics behind all emission nebulae. They are not merely illuminated, they are energized, their very atoms compelled to convert the harsh light of youth into a softer, more ancient glow. Our nebula's story extends far beyond its own glowing borders. It is merely the brightest spark in a much larger, invisible structure known as the Orion Eridanus superbubble. Picture a titanic cavity carved into the galactic plane, a sphere of million-degree gas so vast it could contain thousands of solar systems. This is the superbubble, a cosmic void created not by a single event, but by a chain reaction of stellar violence spanning millions of years. The architects of this immense structure were generations of massive stars that lived fast, died young, and exploded as supernovae. Each detonation sent a powerful shockwave rippling through the interstellar medium, a spherical blast that pushed the surrounding gas outward like a snowplow clearing a road. Over eons, these repeated explosions from a long-vanished star cluster merged their individual bubbles, forging this single, colossal cavity that now envelops the Orion Nebula. We are not just looking at a nursery of newborn stars, but at a structure that was itself born from the death cries of ancient suns. This grand cycle of destruction and creation is the true context for the nebula's fiery activity. The shockwaves from those ancient supernovae did not simply carve an empty space. As they expanded, they inevitably encountered slower-moving, denser clouds of cold molecular gas. The effect was like a hammer striking a cosmic anvil. The shock front compressed the gas, triggering a gravitational collapse in regions that might otherwise have drifted undisturbed for eons longer. This compression is the leading suspect for the very wave of star formation we are witnessing today in the Orion molecular cloud. The nebula, in all its radiant beauty, may be a direct consequence of this ancient stellar carnage. Its brightest stars are the grandchildren of those long-dead giants, their birth catalyzed by a series of cataclysms whose echo still shapes the space around them. This reveals a profound and cyclical truth about our galaxy. The death of stars clears the space and provides the shock necessary to birth the next generation, weaving a continuous tapestry where endings are always new beginnings. Amid all this visible chaos, an invisible force is quietly guiding the show. This is the nebula's magnetic field, a cosmic framework woven through the gas and dust like a ghostly spiderweb. We cannot see it directly, but its presence is revealed by a subtle property of light called polarization. As starlight travels through clouds of magnetically aligned dust grains, its waves become preferentially oriented in one direction. By mapping this polarized light, astronomers can trace the magnetic field structure across the entire nebula, revealing a surprisingly organized pattern. These fields are not just passive decorations, they act as cosmic support beams, providing a crucial pressure that helps vast clouds resist the relentless pull of their own gravity. Without this magnetic support, the entire molecular cloud would have collapsed into stars in a frantic, short-lived burst. Instead, the fields regulate the flow, channeling gas along invisible lanes and slowing the process down to a more sustainable pace. Their influence even extends to the very architecture of newborn solar systems. Many of the protostellar disks we see are not randomly oriented. They show a tendency to align their spin axis perpendicular to the direction of the local magnetic field. It is as if each infant star system is a compass needle, its rotation locked into the invisible grid that governed its birth. This magnetic guidance shapes the entire nursery, from the grandest cloud down to the spin of a single fledgling planet. It is a silent architect, imposing order on the chaos and reminding us that the universe builds with more than just gravity and light. Our eyes capture only a sliver of the nebula's true story. To see the full cosmic drama, we must look with different kinds of light, each wavelength peeling back a new layer of this celestial onion. In the high-energy glare of X-rays, the nebula transforms completely. The soft, glowing gas vanishes, replaced by a sky peppered with brilliant, stabbing points of light. These are the searing coronae of young stars, their outer atmospheres superheated to millions of degrees. Each pinpoint is a testament to ferocious magnetic activity, stellar flares of unimaginable power that make our sun's tantrums seem like a gentle whisper. This X-ray vision reveals the raw, violent youth of these stars, a constant storm of high-energy particles flooding the nursery, switched to the infrared, and the opaque dust clouds that block our visible view suddenly become translucent. The dark pillars and silhouettes fade away, and we see straight into the nebula's secret heart. What was once blackness now glows with the warm thermal radiation of countless embedded protostars, their heat absorbed and re-emitted by the surrounding dust. This is the realm of hidden giants, where stars too young to shine in visible light announce their presence with a gentle, warm glow. Finally, tune into the radio waves, and the frantic stellar activity falls silent. Here, we map the cold, quiet bones of the nebula, vast reservoirs of molecular gas, the raw fuel for future stars, reveal themselves through the faint radio signatures of molecules like carbon monoxide. This is the census of the nursery's deep reserves, the cold, dark material that has yet to feel the touch of starlight. Each wavelength is a different chapter in the same epic, showing us that the beautiful visible nebula is just one face of a far more complex and dynamic entity. These stellar winds are a hurricane of pure energy, flowing from the surfaces of the most massive stars at millions of miles per hour. An O-type star does not simply shine. It actively blasts its surroundings with a relentless gale of charged particles, a force so immense it carves out vast cavities and shapes the nebula's very future. This is the engine of stellar feedback, a self-regulating process where the stars themselves dictate the destiny of their nursery. The energy these winds inject into the surrounding gas is staggering, far exceeding the power of their brilliant light. This energy does not just push the gas around, it superheats it, raising the temperature of the interstellar medium to searing heights. This intense heating has a critical consequence. It dramatically increases the gas pressure. Think of it like a balloon inflating inside a confined box. The rising pressure pushes outward against everything else, most importantly against the inward pull of gravity. This is the fundamental feedback loop. Gravity works tirelessly to pull gas clouds together to form new stars, but these powerful winds create a countervailing pressure that resists that collapse. The entire nebula becomes a battleground between these two titanic forces. In regions closest to the O-type stars, the winds are so ferocious they can completely halt star formation, evaporating protostellar clouds before they ever have a chance to coalesce. They sweep up the raw material of future suns, pushing it into dense shells at the edges of their bubbles, or blasting it entirely out of the cluster. This is why the trapezium's core is a relative void, a cleared-out zone where the most powerful stars have already sterilized their immediate neighborhood. Their violent birth has ensured that no new siblings can form too close. This stellar feedback is a universal governor, a natural mechanism that prevents a star cluster from converting all of its gas into stars at once. It ensures that star formation is a slow, regulated process, not a single, catastrophic burst. The very same winds that give the nebula its beautiful, sculpted appearance are also the force that is slowly, inevitably, shutting down its primary function. That beautiful glow 1,500 light-years away does more than just decorate our night sky. It serves as a fundamental signpost for mapping the cosmos. The Orion Nebula's well-understood distance and brilliant luminosity make it a critical stepping stone in what astronomers call the cosmic distance ladder. This ladder is not a single tool, but a series of interconnected methods, each one building upon the last to measure progressively farther into the universe. You cannot use a single tape measure for everything, from your own height to the width of a continent. In the same way, astronomers need different techniques for different scales. For relatively close objects like the Orion Nebula, the most reliable method is stellar parallax. This works by observing how a star appears to shift its position against the backdrop of even more distant stars as the Earth moves from one side of its orbit to the other. It is the same effect you see when you hold a finger up and close one eye, then the other, watching your finger seem to jump back and forth. That apparent shift, that angle, gives us a direct geometric calculation of distance. The stars within the Orion Nebula cluster are close and bright enough for satellites like Gaia to measure their parallax with incredible precision, pinning down the nebula's distance to an accuracy of just a few dozen light-years. This precise measurement transforms the nebula from a simple object of beauty into a cosmic calibration point. Once we know its true distance with such certainty, we can use it to confirm and refine other, more indirect methods of measurement. For instance, by studying the types of stars in the Orion Nebula cluster and knowing exactly how far away they are, we can calibrate the relationship between a star's true brightness and its color or type. This relationship, once firmly established using a known benchmark like Orion, can then be applied to similar clusters of stars in far more distant galaxies. The Orion Nebula becomes a trusted reference, a known quantity that allows us to confidently leap across millions of light-years. Its familiar glow is the foundation upon which we build our understanding of the universe's vast architecture, a single, brilliant rung on the ladder we climb to reach the edge of the observable cosmos. Perhaps the most iconic image of cosmic creation is an illusion. Those magnificent, towering pillars that rise from the nebula, immortalized by the Hubble telescope, are not the solid, enduring cathedrals they appear to be. In reality, they are dense, fleeting clouds of gas and dust, and their dramatic shapes are defined not by what they are, but by what is missing around them. This is the powerful magic of shadowing. The brilliant ultraviolet light from the trapezium stars is evaporating the entire nebula, but it does not eat away at everything evenly. The process is more like a sculptor working with a block of marble, chipping away the softer material to reveal the form within. The pillars themselves are simply the densest, most resilient knots within the cloud. They are the last to be eroded, acting as vast, cosmic umbrellas that cast long, protective shadows behind them. The material sheltered in these shadows survives longer, while the exposed gas all around is boiled away into the void. What we see as a majestic pillar is actually the shadow of its own dense core, a silhouette of temporary resistance against an erasing light. These structures are not permanent. They are transient, like sandbars in a rising tide. The same stellar winds that define their beauty are also slowly but surely dismantling them. We are witnessing a slow-motion demolition, where the sculptors are also the destroyers. This cosmic chiaroscuro, this play of light and shadow, creates some of the universe's most breathtaking vistas, but it is a beauty born of destruction, a fleeting monument to a battle that the pillars are destined to lose. Long before telescopes revealed its swirling clouds of gas, this patch of light was woven into the very fabric of human story. The nebula hangs like a celestial ornament on the sword of Orion the Hunter, a constellation recognized across the globe. For the ancient Greeks, this fuzzy star was no mere cloud, but a cosmic trophy, They saw it as the glowing shield or club of the mighty hunter, eternally raised against the charging bull, Taurus. But this story was not universal. Half a world away, the Lakota people of North America saw these same stars as a great bison, with the nebula representing its beating heart, a sacred center of celestial life. In Hungary, it was known as the magical sword of King Arthur, its misty glow a sign of otherworldly power. These cultures, separated by vast oceans, all looked up and saw a landmark of profound significance, a point of light that demanded a myth. Its consistent brightness and prominent position made it an undeniable feature of the winter sky, a fixed point in the rotating heavens that every civilization could use to anchor their understanding of the cosmos. This universal recognition made the Orion Nebula one of the first true targets of astronomical inquiry. In the early 17th century, the astronomer Nicolas Claude Fabry de Paris turned a primitive telescope toward the hunter's sword and recorded the nebula not as a single star, but as a mysterious, unresolved cloud. His observation marked a pivotal moment, the first time a nebula was documented as something beyond a star, cracking open a door to a deeper universe. From that point on, this glowing spot became a testing ground for every generation of telescopes, a celestial touchstone that challenged our perception and grew grander with every improvement in our sight. It connects our most ancient stories to our most modern discoveries, a bridge between the myths we tell around a campfire and the profound truths revealed by the Hubble and James Webb telescopes. Our search for worlds does not end with the planets we can see. Drifting alone in the dark spaces between the stars of Orion are true cosmic orphans, objects with the mass of planets yet bound to no sun whatsoever. These are the free-floating planetary mass objects, and their very existence challenges our definitions of how worlds are born. They are not merely rogue planets ejected from a parent star, though that is one possible origin. The sheer number of them found in Orion suggests a more radical possibility. Some of these lonely worlds may have formed on their own, in the same way a star does, from the direct collapse of a small, isolated knot within the nebula's vast cloud. Imagine a pocket of gas and dust that simply lacks the critical mass to ignite nuclear fusion, collapsing not into a star, but directly into a Jupiter-sized sphere of swirling gas. These solitary worlds would never know the warmth of a sunrise, their surfaces perpetually locked in a deep freeze as they wander the eternal night. Their discovery forces us to ask a fundamental question. What truly makes a planet? Is it the fact that it orbits a star, or is it simply a matter of mass? If a Jupiter-sized object forms from a tiny cloud all by itself, is it a failed star or a planet without a system? Orion's dense stellar nursery provides the perfect gravitational chaos to create both types of wanderers. Young, unstable planetary systems can easily fling their infant worlds into the void through violent gravitational interactions. At the same time, the turbulent cloud is ripe with small, collapsing cores that never quite make it to stardom. This population of lonely giants reveals that planet formation is not a process confined to the safety of a circumstellar disk. It is a universal phenomenon that can happen almost anywhere, producing worlds that may forever travel in solitude, dark and isolated, yet hinting at a galaxy far richer in planetary bodies than we ever dream. This beautiful chaos is not built to last. The very forces that give the Orion Nebula its breathtaking glow are the same ones sealing its fate. Over the next 100,000 years, the hurricane of stellar winds and the relentless ultraviolet radiation from its most massive stars will continue their work of demolition. They will systematically blow away the remaining gas and dust, the colorful clouds that make the nebula so iconic. The brilliant red and blue veils will thin, fade, and ultimately vanish into the blackness of interstellar space. What will be left behind is the true skeleton of this stellar nursery, a naked open cluster of stars, shining without any surrounding fog. This future cluster will look much like the Pleiades we see today, a glittering collection of suns, a ghost of the turbulent nursery that once was. But the story does not end there. The most massive stars in the trapezium, the brilliant engines of this destruction, are living on borrowed time. They burn through their nuclear fuel at a ferocious rate, and in just a few million years, they will face their own spectacular ends. One by one, they will explode as supernova. These final, violent acts will be the ultimate dispersal mechanism. The titanic shockwaves from these explosions will deliver the final blow to any lingering tendrils of gas, while also seeding the surrounding space with newly forged heavy elements, the iron and oxygen and silicon, that will one day become part of new planets and, perhaps, new life. The cycle is both beautiful and brutal. The nebula's death gives the cluster its lasting form, and the death of its most massive stars enriches the galaxy for future generations. The Orion Nebula, in all its current glory, is merely a brilliant, fleeting chapter in a much longer story of cosmic renewal. Even the faint, cold dust of the nebula hums with a strange and invisible energy. Across the microwave portion of the spectrum, the Orion Nebula gives off a curious, pervasive glow that should not exist. This is anomalous microwave emission, a mysterious excess of radiation that puzzled astronomers for years. It could not be explained by the usual sources, like the thermal warmth of the dust itself or the synchrotron radiation from high-energy electrons. The culprit, it seems, is the dust grains themselves, but not in the way you might think. These are not ordinary specks of cosmic dirt passively absorbing and re-emitting light. The leading theory suggests they are tiny, spinning nanoparticles, perhaps made of complex carbon-based molecules or tiny flecks of silicate smaller than a virus. When these minute grains are hit by ultraviolet light or collide with fast-moving atoms, they begin to spin at staggering rates, billions of times per second. A spinning charged particle creates its own radiation, and these frenetic dust grains act like countless microscopic radio transmitters, collectively flooding the nebula with the microwave signal we detect. It is a form of celestial static, a faint hiss generated by the frantic dance of the smallest pieces of the cosmic building blocks. This discovery forces us to reconsider the very nature of interstellar dust. It is not just a passive curtain or a simple building material. It is a dynamic, active component of the nebula, its smallest particles contributing to the energy balance in a way we are only just beginning to understand. What other secrets might these spinning motes hold, and what does their universal hum tell us about the hidden life of every galaxy? These young stars possess a hidden temper, unleashing sudden, violent tantrums of X-ray energy. Deep within the Orion Nebula, orbiting telescopes have recorded immense flashes erupting from otherwise calm-looking infant suns. These are X-ray flares, and they are not the gentle, predictable flickers of our own mature star. A single one of these events can release more energy than our sun puts out in an entire year, all concentrated into a few frantic hours. The mechanism is thought to be a cataclysm of magnetic reconnection. Picture the star's tangled magnetic field lines as immense, twisted rubber bands storing colossal stress. When these lines snap and violently reconnect, they release all that pent-up energy in an instant, accelerating electrons to nearly the speed of light and heating vast patches of the stellar atmosphere to temperatures of 100 million degrees. This creates a flash of X-rays so intense it can briefly outshine the star's entire visible light output. For any fledgling planetary system taking shape in the vicinity, these flares are a game of cosmic roulette. The sudden blast of high-energy radiation acts like a sterilizing flash, potentially stripping away the fragile atmospheres of newborn planets or blasting the water and other volatile compounds right off their surfaces. It fundamentally alters the chemistry of the surrounding protoplanetary disk, breaking apart complex molecules that were patiently assembling in the cold dark and forging new, more reactive ones in the searing heat. A planet forming in a system prone to such violent outbursts would have a radically different starting point for life than one born in a calmer stellar neighborhood. This stellar fury raises a profound question about our own origins. Did our sun undergo a similarly violent youth? And if so, did its ancient flares help or hinder the emergence of life on Earth? The unpredictable, searing flashes from Orion's youngest suns remind us that a star's early life is a precarious and explosive time, setting the stage for the future of any worlds that dare to form in its stormy light. From stellar fugitives racing through the void to the faint hum of spinning dust, the Orion Nebula reveals a universe of breathtaking complexity. We have journeyed past evaporating planetary cradles and into the hearts of dark clouds where new suns ignite. We have witnessed how the death cries of ancient stars trigger new births, and how the most violent stellar tantrums can shape the potential for life itself. This single cosmic nursery contains a full spectrum of creation's strange mechanics, from the gravitational chaos that flings stars away to the magnetic frameworks that guide their spin. It is a dynamic, living ecosystem where every force, from radiation to turbulence, plays its part in an endless cycle of construction and demolition. This celestial laboratory offers us a front-row seat to the universal processes that build stars, forge planets, and seed the cosmos with the ingredients for life. The nebula's 30 wonders are more than just a list of curiosities. They are interconnected chapters in the story of how our own world, and perhaps countless others, came to be. Each phenomenon is a vital piece of the puzzle, demonstrating that beauty in the cosmos is often born from violence, and that order emerges from the most profound chaos. So, as this journey ends, we turn the question to you. Which of these strange phenomena captured your imagination the most? Was it the lonely, free-floating planets, the explosive Herbig-Haro objects, or the silent, guiding hand of the magnetic field? Share your thoughts in the comments below. The conversation about our incredible universe is just beginning.